Good afternoon. Today we will start the new chapter, Chapter 9, Atomic Model and Nuclear Physics. In this chapter, we will be discussing different models of atom. We all now know that the whole matter in the universe is made of small atoms, and in this chapter, we will see the attempts of various scientists to discover what is there inside the atom and what is the structure of the atom. And we will come across different models of atoms put forward by J Thompson, then by Rutherford, then Niels Bohr, and then we also will see what are its limitations, why each of these model could not explain all the phenomenon exhibited by an atom. Then we will see nuclear physics. Nuclear physics means the physics of nucleus, which is an important part or the central part of the atom. We will see some nuclear phenomena like radioactivity and also some nuclear reactions like nuclear fission, fusion, etc., where it is used, where it is applied, etc. So this is what we are going to see in this chapter. So let us begin by the first model of an atom put forward by J Thompson. So have you heard of J Thompson? Who is J Thompson? Who is J Thompson? He is the one who discovered electrons. So yeah, in late 19th century, physicist J Thompson began experimenting with cathode ray tubes and eventually discovered the presence of negatively charged particles called electrons inside atoms. So it was J Thompson who first discovered electrons. So until then, the scientists had no idea about the structure of atom, what are there inside the atom. So Dalton put forward the idea that every matter is made of small, indistinguishable, or um, not divisible particles called atoms. And J Thomson was the first one who found out what is there inside an atom. And he found that there are negatively charged particles called electrons inside the atom. Then he started developing a model for atom where he can incorporate the idea that it contains negative charges. So Thomson knew that the atoms had had neutral charge overall. So the overall charge of atom is neutral. So if there are negatively charged particles, there should be a equal or opposing positive charge. Therefore, the atom as a whole is neutral. So what he did was he proposed a new model of atom, which is called the plum pudding model. And according to this model, electrons are negatively charged particles embedded in a sea of positive charge. Like you can see plums inside a pudding. So this is a picture of a pudding and you can see plums which are embedded inside. Just like that, atom consists of a positive cloud or positive sea. And inside that, you have negatively charged in electrons embedded. So these particles are kept inside a cloud of positive charge or a sea of positive charge, and these are separate discrete negatively charged electrons. You can also compare that to the inside of a watermelon. And inside watermelon, what we can see after you cut out all that green part, the skin part, you can see a red flesh, right, of watermelon. So compare that red flesh of watermelon to positive C of positive C, positive charge. So what is inside that red flesh? You can see black seeds. embedded inside that red flesh. So those black seeds can be compared to the electrons which are embedded inside it. So just like black sits inside the red flesh of watermelon, negatively charged electrons are embedded inside the positively charged cloud or positively charged sea. Is this clear to you? What is Thomson model of an atom, which is called the plum pudding model?
Yes.
Okay, so now let us see the next model of atom. Like Thomson's idea of the plum pudding model was not to accepted by the scientific world because it didn't have an experimental base. He discovered electrons, that's true, but he didn't do any particular experiment in order to determine what exactly is the structure of atom. So Rutherford, with his uh, colleagues or with his assistants, Grigor and Modson, did an experiment especially to find out the structure of an atom. And that experiment is called Rutherford's alpha scattering experiment. So let us see the details of Rutherford's alpha scattering experiment, and he did it in 1909. So 1909 he did that experiment. He performed his famous alpha scattering experiment. What is an alpha particle? Have you heard of alpha particle before? You must have learned in grade 10 radioactivity. And in
In
radioactivity,
chemistry.
yeah, in chemistry also you must have learned. And what is alpha particle? Alpha particle is a positively charged particle and it consists of two protons and two neutrons. So two protons have two positive charge and two neutrons are neutral. So it contains two units of positive charge and the mass of the particle will be almost four times the mass of a proton because neutrons and protons have similar mass. So there are two protons, two neutrons. So you can also get an alpha particle or assume an alpha particle as a helium nucleus. Helium. Helium has atomic number 2. So you know that it has two protons and there are two neutrons in its nucleus, right? Now, if you remove the two electrons revolving around the nucleus, what you get is a helium nucleus. That is two protons and two neutrons kept together. It's nothing but an alpha particle. So what you have to remember is that alpha particle contains two protons and two neutrons and it has two positive charge. It is positively charged. Now what did he do? What did Rutherford do? He kept a radioactive source inside a lead container. See, a lead block. He kept the source of alpha particles, that is radioactive particles, inside a lead container. Why lead? Because lead can absorb the radiations, other radiations emitted by the source, and also alpha particles. And there was a narrow opening from where he kept the source to outside, so that a narrow beam of alpha particles can come out. So the narrow beam of alpha particles was made to hit on a very thin foil made of gold. So a thin foil made of gold was kept in the path of this alpha particle. And what happens to the alpha particle beam that comes out of this thin foil of atom was checked by a zinc sulfide screen. This is a zinc sulfide screen, what you can see here. And when alpha particle hits on the zinc sulfide screen means inside the screen there is a coating of zinc sulfide that shows fluorescence. So when alpha particle hits on this zinc sulfide screen, they will produce fluorescence. We can see small flashes of light or scintillations. So whenever the alpha particle hits on this zinc sulfide screen, you can see small scintillations or flashes of light. So this is the experimental arrangement. So what are there? What are the parts used, or what are the apparatus used by Rutherford? You have a source of alpha particle, that is a radioactive material kept inside a lead block. And the narrow beam of alpha particles go and hit a very thin foil made of gold. And around that, there is a zinc sulfide screen. So you know that alpha particles are positively charged. Let us see what are the observations made by him. So the observations made by him is that 99% of the alpha particles go straight, penetrating through the gold foil. They go on straight, which means most of the alpha particles, 99% of the incident alpha particles on the gold foil pass on straight. They are not deflected. Here you can see the same arrangement in a different figure. So there is a polonium sample which is radioactive and which gives out alpha particle, and the alpha particle consists of two protons and two neutrons. They go and hit the aluminum foil. So here when they deviate through small angle, which is shown by theta, there is a movable fluorescent screen and a detector. This detector can count the alpha particles. So from the counts produced by the detector, they could find that 99% of the alpha particles go straight without any deviation, as seen in this figure. And some alpha particles are scattered, making a small angle, which means angle less than 90 degree. Here you can see the blue scintillations of blue lines. Scintillations need not be blue, but this blue lines shows that some alpha particles which deviated from their original straight line path. So some alpha particles, definitely it will be less than 1% of the alpha particles which are coming here. So they got deviated through small angles. Okay. And very few alpha particles were backscattered. Backscattered means deflected with more than 90 degrees. So if these alpha particles were deflected through 90 degree, they should come like this. But some of them got backscattered, came back as if they were hit by a heavy particle. We know that if you throw a ball on a wall, what happens? It will come back. It will get backscattered. So as if a heavy object was in their path, the alpha particles were backscattered, and it was very small amount of them, like about 1 out of 20,000 alpha particles. So a very few amount of alpha particles were backscattered. So this is the experimental arrangement of Rutherford's alpha scattering experiment, and these are the observations made by him. Is this clear to you?
Teacher,
Yes.
why did why did they use the zinc sulfide screen?
They use zinc sulfide screen because the zinc sulfide will produce fluorescence when alpha particle hits on them. You can see light, flashes of light when alpha particle hits on zinc sulfide. That is why. It's a chemical that produces fluorescence when charged particles hit on it. That's why. Okay.
Okay.
So is there any other doubt? Can I continue?
Yes.
Okay, so this is the these are the observations made by alpha particles. See, by alpha particle experiments. See, there are large number of incident beam of alpha particles. So most of them, around 99% of them, go straight, and this is zinc sulfide screen. Using a detector, they are counting the alpha particles that reach them. So this is a gold nucleus, and this is a gold atom. Okay, so when the alpha particles pass through that, gold has an atomic number. I hope it is 76 or 79. So inside the nucleus of that gold, there should be 76 protons. So they can all repel the alpha particles, right? So some of the alpha particles got deviated from their path, and some which of them went and hit the nucleus directly, they must have repelled back scattered, or scattered through an angle bigger than 90 degree. So from all these observations, Rutherford made the following inference, and this inferences led to the discovery of Rutherford atom model, which is also called the solar model. Let us see what it states. Most of the atom is empty space. Since 99% of the alpha particles which were incident on the gold foil went without any deflection, he concluded that most of the atom is empty space. Only then these alpha particles can go without any distractions. They can go through the atom. So most of the atom will be empty space, or around 99% of the atom is empty space. Then he saw that some of them deviated, right? So he assumed that the total mass and all the positive charge of the atom is concentrated in a small space in the center called nucleus. Why he thought like that? Very few only got reflected back or got deflected. They must have deflected when they pass near to the positive charge or to a heavy mass. Okay, so there should be some positive charge should be there, because the atom as a whole is neutral and it contains electrons which are negatively charged. So there will be some positive charge. Unlike what Thomson said this positive charge is throughout the atom. Instead of that, Rutherford told that this positive charge and also most of the mass of the atom will be concentrated in a very small region. If the diameter of an atom is around 10 raised to minus 10 meter, that is about 1 angstrom, then the diameter of the nucleus will be around 10 raised to minus 15 to 10 raised to minus 14 meters. I have just mentioned here 10 raised to minus 15 meter. So it's called 1 Fermi. So if the diameter of an atom is around 1 angstrom, the diameter of the nucleus will be only 1 Fermi. That is 1 by a lakh. So it will be very small. The nucleus is very small. An atom will be 1 lakh times bigger than a nucleus. So most of the atom is empty space, and the nucleus occupies very small place which contains the total mass and all positive charge of the atom. Do you have any doubt on this point? Do you have any doubt? He told total mass. Why he told total mass? We know that there are electrons, they are not there in the nucleus, right? So why still he told total mass or almost most of the mass? Because the mass of the electron is only 9.1 into 10 raised to minus 31 kilogram, while the mass of one proton is 1.6 into 10 raised to minus 27. So 28, 29, 30, 31. See, around 10,000 times massive than an electron. A proton is 10,000 times massive than an electron. Similarly, a neutron is also around 10,000 times massive than an electron. So when you take the total mass of the electrons in an atom, it's negligibly small compared to the total mass of protons and neutrons together. That is why he says that total mass and all the positive charge of the atom is concentrated in the small space in the center, which is called nucleus. So, if the size of the atom is an Armstrong, the size of the nucleus will be a Fermi. So, it's very small. The nucleus is very small and it is in the center. Now the atom is electrically neutral, so there will be electrons present. Now Rutherford had a confusion like where to keep the electrons. He didn't get any information about where the electrons will be from the experiment. So he just guessed that the electrons are revolving around the nucleus. Okay, and the number of electrons outside the nucleus will be equal to number of protons in the nucleus because the atom is electrically neutral. So he guessed that the electrons revolve round the nucleus as planets revolve round the sun, just like this. This is the nucleus. The electrons are revolving round the nucleus in orbits, just like planets revolving round the sun. So this is the solar model, sometimes called the nuclear model as well, put forward by Rutherford. Is this clear to you? How, from the experimental observations, he proposed a solar model for atom. Is that clear? Can I move on? Is this clear to you?
Yes, teacher.
Okay. So this is the Rutherford's model of an atom. But this model was accepted for a long time until the scientific world found some limitations for the Rutherford model. Now let us see what are the limitations of Rutherford model. Now, some of the scientists just told that you cannot compare negatively charged electrons, which are very small, to neutral planets, which are very large. And some told that the force between the electron and the nucleus or the protons are electrostatic in nature. You cannot compare a system where there is electrostatic force which is dominant to another system where gravitational force is more dominant. So that was some kind of discussions that happened between the scientists when you Rutherford put forward this model of an atom. But there was some serious limitations which was noted by scientists till then, that according to then prevailing Maxwell's electromagnetic theory, an accelerated charge particle should emit radiation continuously. So electromagnetic radiations, we have learned what are electromagnetic radiation. It's combination of electric and magnetic field. How are they produced? By accelerated charges. So whenever a charge is accelerated, it is expected that it emit radiation continuously. Now if an electron is making a circular motion, you know that when a particle is having circular motion, it has centripetal acceleration. So it's an accelerated charge particle. So it should emit radiation. So according to Maxwell's electromagnetic theory, since electron is a charged particle which is accelerated, it should emit electromagnetic radiation continuously. So the electrons which are revolving around the nucleus should continuously emit radiations, which means that they will continuously lose energy. So when they continuously lose energy, they should eventually fall into the nucleus. So will the atom exist? No. So Rutherford's atomic model or Rutherford's smaller model failed to explain the stability of atom. So we know that atom is stable, right? This doesn't happen. We cannot find continuous emission of radiation from atom. But we find that electrons emit radiation whenever it jumps from one orbit to another. There are sometimes radiations emitted by an atom, but not continuously. So according to Rutherford's model, the electrons cannot just orbit around the nucleus randomly. In that case, they should continuously emit radiation, which is not practically seen. And also, if they continuously emit radiations, they will lose energy continuously and fall into the nucleus, which is also not seen. So in practice, no radiations are emitted by electrons continuously, and they do not fall into the nucleus, and the atoms are stable. So these things could not be explained by the Rutherford's model. Is that clear to you? What are the limitations of Rutherford's model?
Yes.
Okay, so now Niels Bohr put forward a new theory that can emit these limitations of Rutherford's model. Or in fact, he modified Rutherford's model, but we will see that tomorrow, the next class. Okay?